Hi, everyone, and welcome to our notes on chemical reactions. Today, we're going to be talking about how to identify and balance combustion reactions. So we did talk about combustion reactions briefly in our unit on organic chemistry, but for now, let's just do a quick repeat um, on what a combustion reaction is. So a combustion reaction is one that takes a hydrocarbon, so meaning something that has carbon and hydrogen. It reacts it with oxygen in order to form two things, carbon dioxide and water. That is all a combustion reaction is, and you should just be able to identify it. So here is the symbolic format of a combustion reaction, CXHY. So X and Y can represent any whole numbers, so something like C8H18. That is going to react with oxygen, O2. When a hydrocarbon like C8H18 reacts with O2, those two things will then do what we call combust, or really just means light on fire. And when those two things light on fire, it turns into two new compounds. It turns into carbon dioxide and water. So you've lost the hydrocarbon, you've lost the oxygen, you've made two new things, carbon dioxide and water. That's it. That's all you should know. This is the process, just FYI for those of you that are interested, this is the process that gets used in an engine. So if anybody's interested in cars or just mechanical stuff in general, this is what makes an internal combustion engine work. A hydrocarbon, which is what makes up our gasoline, has to react with oxygen in our air in order to make carbon dioxide and water. But in the process of doing that, we're getting energy out as well, and that energy is used to power our engines or our cars. Okay, so we're going to balance these reactions. Now, the balancing of a combustion reaction is not really any different than balancing any other reaction that we've already practiced, except that you'll notice that you have oxygens in two places in the products. So on the reactant side, you have carbons, hydrogens, and oxygens. And then on the product side, you also have carbons, hydrogens, and oxygens. But the oxygens, there's some oxygen from the water, and then there's some oxygen from the CO2. And that is what essentially will make balancing this just slightly more difficult than any other normal reaction we've done. So in order to balance a combustion reaction, I have a set of balancing rules for you here, and I'm going to go through them step by step as we do some examples. So let's just start with our first example here and set up our REP chart, and then and we'll go through what we should do. So setting up our chart, we're going to list out what elements I have. So I've got carbons, hydrogens, and oxygens. So I'm going to write in carbon, hydrogen, and oxygen. And then if you take a look at my first bullet point here under balancing rules, it tells me to balance my carbons first. So in order to know how to do my balancing, I've got to add up all my carbons, hydrogen, oxygens on each side of the arrow. So I've got 4 carbons on the reactant side. I have 12 hydrogens, and I have 2 oxygens. On the product side, I only have 1 carbon. I have 2 hydrogens, but I have 3 oxygens. I have 2 oxygens coming from the CO2 and a third oxygen coming from my water. So I'm going to write 3 there total. Okay, so in my combustion balancing rules here, I have to first balance out my CO2. So I have I have 4 carbons on my reactant side, only 1 on the product side. I want this to equal 4 so that it balances out what was on my reactant side. So that needs to be 4. How can I make that 4? Well, by putting that 4 in front of the CO2. When I put the 4 there, though, not only does it change how many carbons I have, but it also changes how many oxygens I have. So 4 times that number 2, the subscript on the oxygen, that means I have 8 oxygens from there. But don't forget, I have an oxygen there as well. So I actually have right now 9 oxygens total when I put that 4 in front of the CO2. Okay, so that takes care of step 1. Step 2 then says to balance the hydrogens by now placing some number or coefficient in front of the water if I need to do that. So let's look at my hydrogens. So I have 12 hydrogens on my reactant side, but only 2 on my product side. So I need this to be 12. I want them to both be the same. So in order to get 12 hydrogens, I should put a number 6 in front here. Okay, but again, when I put the 6 in front, that changes this. So 6 times 2, that gives me my 12 hydrogens. But I've also now 6 times the 1 oxygen, so that means I have 6 oxygens. So counting up my oxygens total, I no longer have 9 oxygens. I have 6 oxygens coming from my water and 8 oxygens coming from my carbon dioxide, which now means that I have a total of 14 oxygens. Okay, so now I've taken care of my step 2. Step 3 says to balance the oxygens by putting a number in front of O2. So my carbons have been balanced now, my hydrogens have been balanced now. So lastly, I just need to get this number of oxygens to be 14. So how do I do that? I'm just going to put a number 7 in front of O2. So then I'm just going to put a number 1 here so that I can be very clear. And my coefficients then are just 1, 7, 6, and 4. That's it. So now let's try this one more time. But now the second example is going to show you one step more complicated where we have to use this 4th bullet point here. So let's start out by, again, labeling all my elements here and counting everything up. So to start with, on my reactant side, I have 2 carbons, 6 hydrogens, and 2 oxygens. On the product side, 1 carbon, 2 hydrogens, 3 oxygens. So let's start again by balancing just the carbons first. So step 1 is to figure out how to get my carbons balanced. So this needs to be 2, which means I need to put a number 2 in front of the CO2. When I do that, it changes the carbon, but it also changes the oxygen. So I don't have just 4 oxygens. Don't forget, I also have a 5th oxygen here coming from my H2O. Okay, so step 2 is to balance my hydrogens. I have 6 hydrogens on my reactant side. I want to get 6 on my product side. So what do I need to do to that? I need to put a number 3 in front of the H2O. When I do that, again, that multiplies in there to give me the 6 hydrogens, but it changes this as well. So now I have 3 oxygens coming from my water, and I have 4 oxygens coming from my carbon dioxide for a total of 7 oxygens. So that's my step 2. Step 3 then says that I need to put some number in front of O2 to get these 2 numbers to be equal. So I would hope you would recognize that it's going to be very difficult for me to take some whole number and multiply that number 2 by a whole number to get 7. Obviously, we can't do that. So you can use a fraction here or a decimal in order to do this. But just for a moment, and then we're going to change it up. So what can I multiply 2 by to get 7? I need that to be 7. So there are 2 different ways that I could write this. If I wrote 3.5, that would be the decimal point where 3.5 times 2, that's 7. The other way you could write it as a fraction would be to write 7 over 2 or 7 halves. So either way you would write it, perfectly fine. That would be step 3 there. So 3 halves in front of the O2, or I'm sorry, 3.5 in front of the O2, or 7 halves in front of the O2. Both mean the same. What we're left with is that step 4 says that we can't just have a decimal point or a fraction as a coefficient. So if you have to, because you have an odd number of oxygens in your product side over here, what we're going to do is multiply the entire every coefficient that I see here. So right now, 1, 3.5, 3, and 2. Those are my coefficients. I'm going to actually take everything there, and I'm going to multiply that whole reaction by 2. So now my coefficient in front of the C2H6 is not 1, it's actually 2. My coefficient in front of the O2 is not 3.5, it's actually 7. My coefficient in front of H2 is 6, and my coefficient in front of CO2 is 4. So the correct coefficients for this chemical reaction are 2, 7, 6, and 4. So now if I go and I count all of these things up and I double check that everything balances, it should. I should now have 4 carbons on each side, 12 hydrogens on each side, and 14 oxygens on each side. So you only have to do this step of doubling the coefficients if the coefficient number that you put in front of the O2 has a decimal point or a fraction, like 3.5 or 7 over 2 or 9 over 2 or something like that. That's the only reason you would ever have to do this this 4th step here. That's the only time you're going to use that. Okay, so I would like you guys to try this out on the next few problems, and I'm going to give you a hint. 2 of these problems are going to follow like what you saw me do in this first kind of problem up here, where there should not be any doubling of coefficients. 2 of the problems are going to be examples of things where you will have to double the coefficients in the end in order to get the correct formulas and the correct coefficients. Okay, so let's try the first reaction and see if you can balance it and share your answers with me. Okay, so let's check your work. Did you get 1, 5, 3, 4? If not, stop, go back and see if you can get those totaled up and check your work there. Okay, next one. Go ahead and try number 2. Okay, so number 2 is an example of one where you should have to double the coefficients in the end. So 2, 13, 8, and 10. You had to double the coefficients here because the coefficient that you should have found the first time with the in front of the O2 would have been a fraction or a decimal point. Okay, try number 3. Okay, did you get this as being the reaction where you needed to double your coefficients again? So 2, 5, 4, and 2. All right, that leaves one last example for you. Give it a try. All right, did you get 1, 3, 2, and 2? All right, so if you are finding this to be a little bit difficult, totally understandable, and we can try and do a little bit of extra work with it if you need. These tend to be the most complicated type of balancing because of the the fact that the oxygens are in two separate locations in both the CO2 and in the water, and that's what makes it a little bit harder to balance. So we'll do a little bit more practice with it as we go, but hopefully that makes sense, and I'll see you on the next one.